So hello, my name is Simone Gasparinetti. I work at Chalmers in Sweden, and I'm giving this talk on behalf of our postdoc, Claire Young, who couldn't make it here. It's really unfortunate. She had a visa problem, but I'll try my best to give a good talk on her behalf. My research group is called the 22Q Lab. We are based in Göteborg in Sweden, and we work with superconducting circuits, experiments. We have three main research lines. We do quantum computing with bosonic modes. We do quantum thermodynamics and quantum enabling technologies. If you scan the QR code, you find a list of the talks that you can attend from our students and postdocs at this event. And we're also hiring a postdoc in quantum enabling technologies, so feel free to reach out if you think you're a candidate. I will start by motivating Claire's work, and this is work in the context of quantum computing. And a few years ago, we were discussing quite heavily in our community so-called NISQ processors, so small and noisy quantum processing units. These days, we are migrating more towards larger scale processors and fault-tolerant computing. And one approach to achieve these goals is, of course, to build a larger scale single chip. At the same time, we could also go for a more modular approach in which smaller processors are connected both by classical and quantum channels, the quantum channels providing the key advantage in this scheme. And of course, nothing prevents you to combining these things and having both processors that are large and that are connected by quantum channels in a modular way. Furthermore, there is also interest within a single chip to go beyond the nearest neighbor connectivity. If you think, for example, of quantum error correction with other low parity density codes, for example. So all these considerations motivate the development of quantum channels connecting quantum processing units. And this is one example of how we could think of these quantum channels in the context of a multi-qubit superconducting QPU. We have essentially a quantum channel connecting some qubits that mediate data transfer between data qubits. And we use microwave photons in these channels to mediate the fundamental operations to distribute quantum information, which is quantum state transfer and remote entanglement. There are essentially in the community two main approaches to distributed quantum information. This is a line of work that started back in 2018 with some first demonstrations of deterministic remote entanglement and continues up to today with very many groups contributing. One approach is to use standing wave modes in a coaxial cable. This is an example in which the emitter and the receiver, they are connected by a cable of finite length. If we think of microwave, you can think of maybe a few centimeters up to tens of centimeters. This gives you a free spectral range of hundreds of megahertz, and you can use each of these modes as a carrier of information to mediate the transfer. This is ideal for short interconnects, and you can also devise protocols in which by symmetry there are modes which are dark when it comes to the channel, so the photon loss is mitigated as much as possible. The other approach is to use propagating photons instead. So now think of a very long cable in which now photons are emitted by one mode at the emitter and they are absorbed at the receiver. This is compatible with long distances, and it's also compatible with optical transduction, because you can think of interposing microwave to optical transducers in between and mediate the quantum information from the microwave to the optical and then back, and then reabsorb, and your system would not notice. Unfortunately, this suffers heavily from photon loss in the channel, which is the thing we try to mitigate. So staying on this idea that we are having a waveguide to mediate the exchange of information, there are still different ways we could go about sending these propagating photons. We have seen one such example in the previous talks. In this session, we can use a circulator to break the reciprocity, and this makes it even a short cable look like an infinitely long one. And this is an approach that was used in some of the seminal papers from ETH Zurich, for example, or from Yale already back in 2018. We could also use a very long cable. If the cable is very long, cables up to 60 meters long have been used within a single cryostat for these experiments. Then the free spectral range is smaller than the coupling strength, And then essentially we recover a continuum of modes, and we can still think of photons being emitted by one node and received by the other. Finally, and in a complementary way, we could also use directional emission. And for example, if we prepare a coherent superposition of two qubits that are placed at a given distance in the waveguide, we can arrange it in such a way that the photons would be emitted predominantly in one direction. And this also makes for an interesting and modular architecture to distribute informations using a waveguide. So our work that Claire did in distributed quantum computing, it consists of these three main results. We've been working about temporal shaping of microwave photons, and this is very important because it facilitates a reabsorption of the photon at the receiver. And then we've been working with frequency-bin-encoded microwave photons and as one approach to enable photon loss detection. And as a result, boost the fidelities that we have when we want, for example, to create a Bell pair. And finally, we have also explored a minimal setup to generate continuous entanglement just by driving a two-level system continuously. And this is a minimal hardware that we can think of to generate entangled modes in microwaves. And today, I will focus in this talk on these first two contributions. So our experimental platform is actually very simple. We use emitter and receiving units as building blocks. And one such unit consists of two qubits connected by a tunable coupler. The data qubit hosts the information, and the emitter qubit is strongly coupled to a waveguide. And there you can see a micrograph of the sample, and the tunable coupler will have a squid and a flux line to drive it. This is actually a pretty outdated and conventional design. It's a very solid one. The way this works is that we are going to be preparing a coherent superposition in the qubit, and via this emitter qubit, we're going to transfer it into a single rail photon. So the coherent superposition between G and E in the qubit is mapped onto a coherent superposition of 0 and 1 Fock states in a propagating mode in the waveguide. Finally, instead of reabsorbing the mode, we can directly look at propagating microwave photons and do operations such as state tomography and also quantum process tomography directly on the propagating mode using linear amplifiers. And this is something that is known in the field for a bit more than 10 years now. So not only can we look at the qubit state, but we can also directly look at the state of propagating modes. We tune up and drive the parametric coupler in a quite conventional way. Here you can see a plot of the frequency of the three modes of interest as a function of the flux in the coupler. So you can see the coupler frequency is the one that tunes the most. And we're going to pick a working point in the coupler, denoted by the arrow. And we're going to parametrically driving the coupler at the frequency difference between the data and the emitter to initiate coherent population transfer. The choice of the working point is given by a trade-off between the Purcell decay of qubit 1 into the waveguide and a larger coupling strength. We can get a larger transfer efficiency if we move the coupler closer, but then the first qubit, which we want to be long-lived, starts to decay into the waveguide. This is a slightly different trade-off that you typically have in these systems. Usually you're worried about ZZ interactions, but not here because the emitter qubit is always empty. So this trade-off is slightly different here. To initiate population transfer, we parametrically drive, and this is a plot. Once we prepare the data qubit in a coherent superposition and turn on the exchange mechanism, we can directly look at the waveguide, what comes out. So this is a coherent amplitude of the outgoing field for three selected values of the strength of the drive. And we can see that the speed at which the excitation is released increased as the amplitude of the drive is increased until we reach a point, and this is the green triangles, in which we start having recurrences. And you can understand this very simply as an interplay between the coherent exchange and the decay into the waveguide. If the coherent exchange is too strong, excitation flows back and forth between the two qubits, and we start to see these recurrences. So the optimal driving strength is something in between the yellow and the green. So this happens when we drive the coupler at constant amplitude. And now the first ingredient I want to introduce here is the photon shaping. So what does photon shape mean? It means that we're going to control actively the temporal envelope of the emitted photons, instead of just accepting what we get here by driving at a constant amplitude. This is achieved by modulating the decay rate in time, which in our case is achieved by modulating in time the strength of the parametric drive. Photon shaping is something which is necessary to facilitate reabsorption at the receiver, because an emitter accepts with unit probability the time reverse version of the things that it emits. And this is why symmetrical envelopes are ideal in this context, because they split the work evenly between the emitter and the receiver. If I emit a symmetrical envelope, I could use the very same building block as a receiver. I'm just going to play the same pulses in a time-reversed way, and the photon will be absorbed with a probability close to 1. This is quantified by symmetry parameter, which is unfortunately missing in the slide, but it's essentially the scalar product of the waveform with its temporal inverted version. So let's look at photon shaping. We start with the unshaped case, in which the data qubit is prepared in a state of superposition and the coupling drive is just turned on. This results in a temporal mode that has a finite rise, but then decays exponentially, as expected. If we compute the symmetry parameter for this particular waveform, we find 84%. Then we can try to tilt the amplitude of the coupler so that the waveform becomes more symmetric. Essentially, we want to delay the emission in the beginning, and we want to make it faster in the end. And if we do that, we achieve quite a symmetry in the waveform, as you can see by the red trace. However, when we compute the symmetry parameter, we got an even worse result. Now we're down to 60%. And the trick is not just to look at the amplitude, but also the phase. It looks like when we change the amplitude of the coupler, we have introduced a significant phase distortion. This is evidenced by the blue line, which is quite straight in the left, but quite tilted in the middle. Why is this happening? The explanation is quite simple. Once we start parametrically modulating the coupler, we are changing its average frequency, and we're also changing the dispersive pull on the emitter and data qubit. So we're introducing a time-dependent frequency shift that causes a phase to roll. And so we have to take that also into account. So in the next experiment, we actively compensate for the phase by turning to a full vector modulation of the drive. And once we do this, we can achieve both a symmetric temporal envelope and a constant phase. And once we compute the symmetry parameter, now we're 98%, so we are pretty good. So to characterize the emitted photon state, we resort to temporal mode matching. Temporal mode matching is a technique to single out a single mode out of a continuum. It is formally defined by that integral that we see over there. Using temporal mode matching, which means essentially that we acquire the signal and we integrate with a given weight given by this function f of t, we can compute different moments of the emitted photon field. We are looking at a tiny quantum signal sitting on top of large noise induced by our linear amplification chain. So there are advanced techniques that we do to reject the noise under the assumption the signal and noise are uncorrelated. That operator H dagger over there, it stands for the noise modes. So this is a plot of the selected moments of the emitted field as a function of the Rabi angle in the preparation of the data qubit. We can see, for example, in the middle, if the preparation angle is pi, corresponding to a pi pulse, the moment A dagger A reaches its maximum. This is because we have prepared one photon with certainty. On the other hand, a single photon has a random phase. So when we look at the blue trace, which is the average of the moment A, this goes to 0. By contrast, if we look at the pi over 2 pulse, then we have the maximum phase information. And this is a maximum of a blue curve at 0.5 pi over there. Based on these moments and on maximum likelihood, we can reconstruct the density matrix of the propagating mode. And this gives us access to full quantum state tomography and process tomography. So here I show, for example, quantum state tomography of two selected states when we try to prepare a coherent superposition or a single Fock state, and with fidelities in the range of 97 to 98%. And finally, I can also look at the quantum process tomography of the transfer of information between a stationary and the propagating mode. So I'm looking at the identity operation here, and the fidelity of this transfer is 94.5%. So this concludes our overview of the photon shaping techniques, but however, we know that these single photons, they get lost easily. And we've been working a lot to mitigate losses. We've seen previously in this talk that you can actually achieve over 90% transfer efficiency. So these numbers I'm quoting here, maybe they're a little bit on the low side, 60 to 70%. Maybe we can push it to 90%. But the fact is there is significantly more loss on these channels than there is in the QPU. And this is limited by, for example, the choice of components, the circulator, the connectors, and so forth. So how can we preserve high fidelities in these remote operations in the presence of this significant photon loss? That is a question. And one interesting approach to this is that we're going to transfer not just a single photon, but directly an error-correctable state. For example, if you're working with bosonic processors, you can transfer a binomial code. And then if you lost a single photon, you can detect that error and you can correct. This is, of course, challenging for conventional QPUs that work on discrete variables and single qubits. So what you could do instead is that you could use a dual rail approach. Using a dual rail approach, you would convert the photon loss into an erasure error. So you can detect whether you lost a photon. And then essentially, you don't have to encode your fragile quantum information directly in that state. You could, for example, repeat the protocol until success, until you've created a Bell state with high fidelity, and then consume this Bell state in your computation by teleporting gates, for example. So this is the idea that we have in mind here. There is, of course, several flavors of dual rail encoding. The most common are the time-bin, the frequency-bin, and the spatial-bin, or path encoding. Path encoding is most common in optics, arguably, and in our community, we've been exploring mostly time-bin and frequency-bin. In time-bin encoding, the time of arrival of the photon encodes the information. So logical 0 is a photon arriving early, and logical 1 is a photon arriving late. In frequency-bin encoding, by contrast, it's a frequency that encodes. The photon can arrive at the same time, but they carry a different frequency so that they can be distinguished. And these things, of course, they can also be mixed because one can look at orthogonal time bins, as we will see probably later in this session. Looking at time and frequency-bin encoding in the literature, there have been a few experiments in time-bin encoding. In one such experiment, essentially, we need a structure that looks like the level scheme over there. We are using one more state of a transmon qubit, the state F, so we can transfer the quantum information from the GE subspace to the EF. And then we use the E state as a buffer. And then the states that go to F, they can be transferred to G1, where 1 is a Fock state of the emitter, and then the emitter will decay and release. So we need an extra state to park the information so that we can go one after the other. And that state is the E state. So first we move the F state and release a photon, and then we carry the residual information in E to F again to emit the second one. So in this way, you can detect photon loss. When we look at frequency-bin encoding, which is this work, we emit the photon at the same time. So we can detect the photon loss just as well, but we are going to be twice as fast because we don't need to wait to emit the second photon. We're just going to be emitting it at a different frequency. So how do we do this? We need two different states to emit, and we need two simultaneous transitions to encode this information and transfer them into these states that will release the photons. And of course, a simple way to do it is just to duplicate what we had already. So essentially, having two identical units, as I've shown before, coupled by an element, and have each of these units individually emit a photon at a different frequency. This is not very hardware efficient. However, it needs 4 qubits and 3 couplers just to enact this operation. And so that's not the approach that we went for. We found something that is more hardware efficient and in a sense optimal in terms of the number of states that are involved. And we're looking again at our qubit coupler qubit structure. Look at the scheme below, for example. But now we are going to put the coupler and the emitted qubit in resonance. So they are going to form strongly hybridized mode with the coupling, with the splitting of around 100 megahertz. And now, because of this strong coupling, we have created a symmetric and an antisymmetric states 100 megahertz apart, which are both strongly coupled to the waveguide and coupled to the data qubit. So this way we have fulfilled the first of those two requirements up there, that we have two different emission states, which are the two hybridized states. Now we need to find two simultaneous transitions to address these states at the same time. And to do so, we have looked at two transitions that some of us have used in the literature. One is a parametric drive, and the other one is a higher photon transition. One of these transitions is going to bring the E state of the qubit to state A. This is essentially an I swap. And the other transition, which some of you know as F0G1 transition, it's going to bring the state F of the qubit into a state in which the qubit is empty and the symmetric mode is occupied. And we're going to drive these at the very same time. So this fulfills the second requirement. This is a bit more of a detailed level scheme how this happens. So we start in the GE subspace of the qubit encoding the information. Then we transfer it to the EF. And then we're going to fire from E into A and from F onto S. And both of these states, they will decay at a different frequency. One of these interactions is a parametric drive, and the other is a second order direct transition. So we're using a charge line for one and a flux line for the other. And ultimately, this is what is happening. So we can characterize the results by driving these two things at the same time and imaging the propagating photonic modes. And these are the modes that we get. We're not combining this technique with photon shaping yet. So we're using constant drives alone. And here are the temporal envelopes that we get. And out of these, we can do temporal mode matching for both modes at the same time. And we can look at selected moments. We can look, for example, at the photon occupation and at their correlations. One thing that you might notice if you take a moment to analyze this plot is that the photon numbers, they are not where they're supposed to be. There's a photon number in one mode that's supposed to start at 0, and it starts at about 15%. And when we looked at the data later on, we find out in that cool down, we had 14% thermal occupation of the qubit, which has nothing to do with this protocol. So it's very unfortunate that this is the best data we can present. However, we have taken this into account when we do quantum process tomography. I was personally quite surprised that you can do quantum process tomography starting from mixed states, but our theorists have worked it out. And if you know exactly what mixed states you have, turns out you can still do it. And if you're interested in this problem, look at the supplementary information. And if you disagree with us, feel free to reach out. I thought it was an interesting problem. Nevertheless, based on these considerations, we can look at the process fidelity, and we find a fidelity of 94.9% for this process. And this is mainly limited by the coherent time of the qubit and the coupler. The coupler, in particular, has a quite low T1 of 1.5 microseconds. There is probably also a small coherent error due to the fact that we drive this at the same time, but we take as good care as we can in, for example, compensating for stark shifts and other things. So I'm going to go a little faster here. Essentially, once you have an emitter like this, and if you add photon shaping, so these are the two ingredients I presented, you can run a protocol in which the absorbing qubit does the exact same thing as the emitter, just time reversed. And then you're able to detect photon detection. You're able to detect photons, as you see in that table below. In the case the event is successful, you have successfully transferred the information, but if you lost the photon, you look at the bottom right, the receiver ends up in the F state. And now you can do a QND measurement, which is selective on the F state, not looking into the GE subspace, and you can herald whether you lost the photon or not. If you lost it, you try again, and if you don't, you have the information stored in the GE subspace of the receiver. Yes, I think I'm going to go a little faster. I just want to say that this technique is a building block. It can be combined with other things. For example, you could look at time frequency cluster states, and it's also very compatible with dual rail qubits, because this is naturally a dual rail approach. If we look at the future of distributed quantum computing, we may look at both short distance and long distance interconnects. Short distances might be within a cryostat or maybe within cryostats that are connected by cold links. And this is what the future data center, quantum data center might look like. And then for long distance interconnects, most likely we have to go to optics. And this is why we're looking forward to developments in microwave to optical transductions here, and what sort of algorithm you can play. And most likely you will need a form of loss heralding mechanism, which we have in place with this approach. In conclusion, we demonstrated frequency-bin encoding in the microwave regime for the first time. This implementation is quite hardware efficient. I think we're using the least number of states we could possibly do to achieve this. It should be easy to integrate it with conventional QPUs. It's compatible with dual rail, and it's also forward-looking in terms of microwave to optical transduction. So I'll stop here and take some questions. Thank you.
Thank you. Very nice talk. If you eventually aim to shape these photons, how big of a challenge is doing this given the two shifts that you get from the two transitions and even cross effects between the two of them?
Right. In the old times, I would have said this is challenging. These days, I'd say let's look at reinforcement learning or other techniques like this, which is always the best when you want to give the final tweak to these. So that's how I would do it today.
Hi. When you strongly hybridize the coupler and the emitter qubit, do you observe any extra dephasing? And do you have like a way of fixing for that?
Yeah, coherence is not the best. At some point, you might also be worried about Purcell decay, because now you're bringing essentially the other mode very close. So maybe you want to add a Purcell filter at the output.
Very nice talk. I think I missed a little bit the pros and cons between frequency bin and time bin, and especially since you had a look at microwave to optics transduction in your outlook, I feel that time bin is much easier for them, for that community. Can you comment a bit on this choice?
In the most, let's say, in the most straightforward approach, frequency bin is twice as fast because you don't have to wait. Then when you go to optics, then okay, then you have a problem. Are you kind of going to use different paths, or are you going to use different modes? Are you going to use two transducers? This is a bit far-fetched. Thank you.
I had a question about your photon envelope shaping. How limited are you by distortions in like your control lines? Like, do you characterize how, like, when you try and send one of those amplitude signals, how like faithful it is to what you want?
It's interesting. When we do parametric modulation compared to baseband pulses, we're generally less sensitive to that because these pulses are still very narrow band. So I don't think, and the time over which we do it, you see it's quite long, is almost a microsecond. So it's not much of that here.
Thanks for the great talk. So I think, like I said, pulse shaping is kind of getting closer to like being useful. Do you also have to compensate for effects of dispersion in the waveguide? And is that something that's easy to do?
I think this is a very interesting question. And of course, in principle, that's also something that you could let an agent fine-tune once you have a way to look at the fidelity of the receiver. But we haven't tried actually to receive anything, as you see, so we don't know yet.